Okay, now that we have finished the Taylor series, we can see how we can use it in multiple dimensions and incorporate it in our Kalman filter. Let me remind you, the Kalman equations in the linear form say the following thing. X, the state vector at k plus 1, equals F, the transition matrix, times xk. And Z at time k equals H, if you remember, the matrix that convert the state space into the sensor space times xk. Of course, plus noise, of course here, plus noise. But, and this is important, when we are in a nonlinear world, this F matrix can become an arbitrary function of any type that we want. And then we can write those equations in the following way. So x at k plus 1 equals f of xk. And f means an arbitrary function, and it doesn't have to be a linear function, of course, plus noise. And z at time k equals h, an arbitrary function of xk, of course, plus noise. The two functions that we see here are nonlinear. And what we will have to do is to take those two functions which affect our whole state vector and make a linear approximation out of them. If you remember from Taylor series, if we'd like to compute f of x, and this is x and this is a, and we expand the function around a, what we end up with is a linear approximation around a, and then we can approximate f of x. So we end up with f of x is approximately equals f at point A plus the derivative of f at point A times x minus a. And this is basic Taylor series. Now we want to take this function and convert it or expand it to multiple dimensions. Let me demonstrate it on the H function or the H matrix. What I get is the following. H of x equals h at point mu, and we always expand this around the point mu, which is the point with the most samples, the point with the most examples. What do we do here? Just like the one-dimension Taylor series, when we expand around point A, which is the most important point, now we expand around mu. Why? Because this is Gaussian, and when you deal with Gaussians, you assume that most samples will be clustered around the mu, around the mean, and this is important. So the best way, the best point to expand, to approximate the function around is the mu, and we have covered it already in the previous videos. Now, what we have is h at point mu plus, and this is important, dh to dx at point mu times x minus mu. This part over here is vector because x is a state vector and mu is also a vector. But this part over here, this part is called the Jacobian matrix. Now, if you inspect this matrix, you will find out that h, ij, row I and column j, equals the partial derivative of hi to xj times xk. So in the first row, we have dou of h1, the partial derivative of h1, the partial derivative of h1, the partial derivative of h1, and each column is the partial derivative of h1 with respect to x1, with respect to x2, with respect to x3, all the way to xn. And in the second row, we have the partial derivative of h2, the partial derivative of h2, etc., etc., again, with respect to x1, x2, x3, x4, till xn. In essence, the Jacobian matrix is a sum of all partial derivatives. Notice that in the first row, we have the partial derivative of h1, in the second row, we have the partial derivative of h2, and in the third row, we have the partial derivative of h3, and so on and so forth. In the first column, we have the partial derivative with respect to the first element in the state vector x1. In the second row, we have the partial derivatives with respect to the second element in the state vector, x2, and so on. Let me give you a concrete example dealing with the F matrix. In this example, we have a bug, and this bug is walking away from the sink. Now, it has a sensor that measures the lateral distance between it and the sink. So we get, this is a distance at time t, this is a distance at time t plus 1, and this is a distance at time t plus 2. And of course, it has constant orientation and constant velocity. So, if I define the state vector as having three parameters, d, the lateral distance from the sink, theta, the orientation, and v, the velocity, then I end up with x at k plus delta t as d plus delta t times v times cosinus theta, theta and v. Why? First, because theta and v are constant. But what about d? So please watch this equation. D at time t plus 1 equals d plus lambda, but lambda equals d times cosinus theta, but d equals v times delta t. So this is a nonlinear function. Why? Because cosinus of theta is nonlinear. What do? We utilize the Jacobian matrix. So again, if we utilize the Jacobian matrix, what do we need? We need f1, f2, and f3, and we need x1, x2, and x3. Let's write those equations. So we have three f's, f1, okay, and this is the first f, f2, and f3. And we have three parameters, or three x, x1, x2, and x3, which are d, theta, and v. What do we do now? We derive each function with respect to all three parameters. Let's start. We have the partial derivative f1 in the first row, each with respect to a different x, x1, which is d, x2, which is theta, and x3, which is v. So let's derive it. If I derive the first function, d plus delta t times v times cosinus theta with respect to d, then I end up with 1. Why? Because it's just like deriving x plus c with respect to x. C is constant, so it doesn't matter, and when you derive x with respect to x, you end up with 1. Now, what happens when I derive the first function with respect to theta? I end up with minus delta t times v times sine of theta. And when I derive it with respect to v, I end up with delta t times cosinus theta. And this was the hardest thing. Now, everything is going to be very easy because everything is going to be linear. When I derive f2 with respect to d, I get 0. When I derive f2 with respect to theta, I get 1. And when I derive f2 with respect to v, I get 0. And basically, it's exactly the same over here because all I need to do is to derive v with respect to v. So this is a Jacobian matrix f that we got from the arbitrary nonlinear function f. In this video, we emphasize the f Jacobian matrix, and in the questions below, we will do the same thing for the h matrix. We will take an arbitrary nonlinear h function and derive an h Jacobian matrix out of it. Good luck!